Normally, when you connect an STM32 board to your computer, it just sits there as a microcontroller. But in this video, we'll turn the STM32 into a real USB device that appears as a virtual communication port on the computer. We'll send data directly over USB, use printf without UART hardware, and understand how the STM32 USB peripheral actually works behind the scenes. Welcome to Controllers Tech. In this video, we are starting a brand new series on the USB peripheral of the STM32 microcontroller. Throughout this series, we will work with different USB classes, including the communication device class, the storage class, the human interface device class, and the device firmware upgrade class. Today, in this first video, we will focus on the communication device class, or CDC. The STM32 will act as a USB device and communicate with your computer through a virtual communication port, no extra hardware, no USB-to-UART bridge, just a single USB cable. We will also cover USB hardware availability across different STM32 development boards, how to configure the peripheral in CDC mode using STM32CubeMX, and how the peripheral behaves when the USB cable is disconnected and reconnected during operation. Let's start by understanding USB availability across different STM32 boards. I am going to use the STM32F446 development board by React Studio, which has a single USB port on it. This port can be used in either host or device mode, and we will be using it for this video. Since it is a custom board, it does not have a dedicated ST-Link USB connector, and this is a pattern common to most custom development boards you will find. Here is another board from MCU Dev, an H7-based development board, and as you can see, it also has a single USB port, that can be used in either host or device mode. Now here we have the well-known Blue Pill board, which also has a single USB connector. However, on the STM32 Blue Pill, the USB can only be used in device mode. The key point with all these custom boards is that they each have one USB port, and that port can be programmed to operate in different USB classes depending on the application. Now let's look at the Nucleo boards from ST Microelectronics. On a standard Nucleo board, you will notice a USB connector at the top, but this connector is exclusively allocated to the ST-Link and cannot be used for USB communication. It is important not to confuse the two. On Nucleo boards, you can still use a virtual COM port through the UART over ST-Link, but that is a separate feature and unrelated to what we are doing in this series. For USB peripheral communication on these boards, you would need to connect an external USB connector directly to the USB pins of the microcontroller. However, not all Nucleo boards require this workaround. Some Nucleo boards come with two USB connectors. For example, the Nucleo 144 board generally has two USB connectors on it. The one near the small onboard MCU is the ST-Link connector, while the one at the far end of the board is the user USB connector, which can be freely programmed for USB communication. You will also find a label on the board reading user USB next to that connector, making it easy to identify. Discovery boards from ST similarly tend to come with two USB connectors, one for ST-Link and one available for the user. So depending on the development board you have, make sure you are using the correct USB port for communication. To be clear once more, on standard Nucleo 64 boards, the second user USB port is generally not available, so you cannot directly connect a USB cable for peripheral communication. The ST-Link USB cannot be used for USB programming or communication purposes. With that understanding in place, let's go ahead and create a new project in STM32CubeMX. As mentioned, I will be using the STM32F446 microcontroller for this video. But before we proceed, let me briefly go over the board schematic, because there are a couple of important things to note. This is a React Studio board, and here is its schematic. There are two things I want to highlight. The first is the clock. The board has an 8 MHz crystal on it, and I will be using this crystal to provide the main clock for the MCU. The second thing to note is the USB interface. The board uses a USB-C connector, and the USB data pins are connected to PA11 and PA12. This pin mapping is common across most STM32 boards, but it is always a good idea to cross-check the reference manual just to confirm the pin connectivity for your specific board. Now let's go back to STM32Cube and continue setting up the project. The first thing we need to do is enable the external crystal oscillator to drive the system clock. The board has an 8 MHz crystal, and we will use the PLL to scale this up, and run the system at the maximum possible clock frequency of 180 MHz. That is all we need to do on the clock side for now. Going back to the pin configuration, enable serial wire debug under the system core configuration. Next, open the connectivity section. Here you will notice that the STM32F446 has two USB peripherals available. The first is USB-OTG-FS, which stands for full speed, and the second is USB-OTG-HS, which stands for high speed. The high-speed peripheral typically requires an external PHY chip to operate at true high speed. If you enable the external PHY option, you will see that a large number of pins get automatically assigned in the pinout view. Since we do not have an external PHY on this board, we will not be using that option. The HS peripheral does also support an internal full-speed PHY, which allows it to function as a full-speed peripheral without an external chip. However, in this configuration, the USB pins used are PB14 and PB15. According to the board schematic, we know that the USB connector on this board is wired to PA11 and PA12, so this configuration does not match our hardware either, and we should not use it. Therefore, throughout this series, we will be working primarily with the USB OTG, full-speed peripheral, whether on the F446 or the Blue Pill board. The full-speed peripheral is the more commonly used one, and most development boards already have a USB connector soldered and wired to the full-speed peripheral pins, making it the practical choice for the majority of USB applications we will cover. Since we want to use the USB peripheral in the communication device class, or CDC, let's go ahead and enable the USB OTG-FS peripheral in device-only mode. Once you do that, you will notice that pins PA11 and PA12 are automatically configured as the USB D+ and D- data lines, which matches exactly what we saw in the board schematic. So the pin mapping is correct. Now, you will notice that the clock configuration is showing an error. This is happening because the USB peripheral is currently receiving the full 180 MHz system clock, which is not correct. The USB peripheral requires exactly 48 MHz to operate properly. So we need to go into the clock tree, and adjust the multipliers and dividers accordingly. You have a few options here. You can reduce the overall system clock, adjust a specific multiplier or divider in the clock tree, or change the clock source entirely. The right approach depends on your specific clock tree setup and what fits best for your application. I have gone ahead and made the necessary adjustments, and we now have exactly 48 MHz going to the USB peripheral while the system clock continues to run at the maximum, 180 MHz. Now let's go back to the peripheral parameter configuration and go over a few things. In full speed mode, the USB peripheral communicates at a data rate of 12 megabits per second. In high speed mode, that rate goes up significantly to 480 megabits per second. However, as discussed earlier, we will be working exclusively with full speed mode throughout this series. There are a few additional parameters visible in the configuration. The low power mode allows the USB peripheral to enter a reduced power state during inactivity, which is useful in battery-powered applications. The linked power management mode is an extension of that, enabling more granular power state negotiation between the USB device and the host. The V-bus sensing option allows the peripheral to detect whether a USB cable is physically connected by monitoring the V-bus voltage line. The SOF, or start of frame output, is typically used in applications that require precise USB timing synchronization, such as audio devices. None of these features are required for a basic CDC implementation, so we will leave all of them disabled for now and keep the configuration straightforward. Now go to the middleware section. Since we configured the USB peripheral in device-only mode, you will see that only the USB device configuration is available here, which makes sense. Now select the class for the USB device and set it to the communication device class. This will make the STM32 appear on the computer as a virtual COM port, allowing serial communication over USB. Let's quickly go through the available configuration parameters. The maximum number of configurations defines how many different operating modes the USB device can present to the host during enumeration. For example, a device could expose one configuration as a virtual COM port and another as a mass storage device. In most STM32 USB projects, we only use a single configuration, so we will keep this set to 1. The maximum number of interfaces defines how many USB functions can work simultaneously inside that configuration. For example, a composite USB device could have separate interfaces for HID, CDC, and MSC working together at the same time. In this tutorial, we only need a single interface, so we will keep it set to 1 for now. In the upcoming tutorials, we will add more interfaces to build composite USB devices. The maximum size for string descriptors is set to 512 bytes, which covers all the text descriptors the device sends to the host, such as the manufacturer name, product name, and serial number string. The USB self-powered option is enabled, which tells the host computer that the STM32 board has its own external power source and does not rely on the USB bus for its main operating power. For example, the board may be powered through a regulator, battery, or separate DC supply while USB is only used for communication. This information is sent to the host during enumeration, allowing the host to manage USB bus power allocation more efficiently. The debug level should be set to 0 since we will not be using any USB debugging in this project. Now for the buffer sizes. By default the receive and transmit buffers are set to 2 KB each. Since we are not doing any high throughput data transfer in today's video, let's bring both down to 512 bytes. Keep in mind that larger buffer sizes allow more data to be transferred at once and can improve communication speed, but they also consume more RAM. So adjust these based on the needs of your specific application. Finally, go to the Device Descriptor tab. Here you can see the information that the device will present to the host computer when it is first connected, such as the vendor ID, product ID, and device description strings. We will leave all of these at their default values for now, and not go into too much detail on this tab. We also need to configure a GPIO pin for the onboard LED. I am setting pin PB2 as a GPIO output. If you refer back to the board schematic, you can confirm that PB2 is the pin connected to the onboard LED. We will use this LED to visually verify that our USB communication is working. Specifically, we will control it by sending a command from the computer over the USB virtual COM port. That covers everything we need to configure in CubeMX. Let's move to the Project Manager tab, give the project a name, select STM32CubeIDE as the toolchain, and click Generate. The project has now been generated. Let's import it in the STM32CubeIDE. As you can see, the project has loaded successfully. All the USB-related source files are organized under a dedicated folder called USB device. Out of all the files in this folder, The one we care about most is USB CDC if.c file. This file is solely responsible for handling all USB CDC communication. Inside this file, you will find the RX and TX buffers defined at the top. Below that, there are several functions related to CDC communication. An important thing to note is that most of these functions are declared as static, meaning they are scoped to this file and cannot be called from outside it. The function we are most interested in for receiving data is CDC receive FS. This function is called automatically whenever the host sends data to the STM32 over the USB virtual COM port. Since it is a static function, any code that handles incoming data must be written inside this file directly. We will come back to that shortly. For transmitting data from the STM32 to the host, there is a separate function called CDC transmit FS. Unlike the receive function, this one is not static, which means it can be called freely from any other file in the project. So, let's start with transmitting the data using this function first. We will implement the transmission from the main file. Open the main.c file, and at the top, include the cdcif.h header file. This gives us access to the CDC transmit function from within the main file. Now, inside the while loop of the main function, call CDC transmit fs to send the string hello world every 1 second. Let's build the project. You will notice a warning after building, and this is because CDC transmit function expects a pointer to an unsigned integer as its data argument, but we are passing a character string. To fix this, simply add a typecast to the unsigned integer pointer before the string. After doing that, the build completes with no errors or warnings. Let's flash it to the board. The project has been flashed successfully. Now to view the data being transmitted over USB, we can use any serial monitor application on the computer, the same kind we would use for regular UART communication. Here I am using the WCH serial software on Mac. At the moment, you can see that no USB device is being detected. Now let me plug the USB cable into the STM32 board. And just like that, the device appears. Let's connect to it, and as you can see, the hello world string is printing on the console every 1 second exactly as expected. One notable advantage of USB virtual COM port communication over traditional UART is that the baud rate setting does not actually matter. You can set any baud rate in your serial monitor, and the communication will still work perfectly, because the data is transferred over USB regardless of that setting. Now let me unplug the USB cable. As you can see, the device immediately disappears from the serial monitor, and is no longer detected by the computer. When I plug the cable back in, the device reappears and resumes transmitting data without needing any baud reset. It just works. However, this plug-and-play behavior may not always work the same way across all setups, which is something we will address as we move forward. Now that we have transmission working from the STM32 to the host computer, let's go ahead and implement the receive functionality as well. The CDC receive function stores incoming data in a buffer called user RX buffer, which is defined inside the cdcif.c file. To access this data from the main file, we need to declare it as an external array there. Now, as mentioned earlier, the CDC receive function is static, so the actual reception handling must happen inside the cdcif.c file itself. In order to access the received data from the main file, we will define 2 additional variables, a flag that gets set when new data arrives, and a variable to store the length of the received data. We will declare both of these as extern in the main file, and define them properly inside the cdcif.c file. So go inside the file, and define both variables there without the extern keyword, since this is where they actually live. Now inside the CDC receive function, after data has been received, set the flag to indicate that new data is available, and store the received data length in the length variable. That is all the modification needed in the CDC file. Now go back to main.c. Inside the while loop, add a check for the received flag. When the flag is set, we will process the incoming data. In this example, we will use the received data as a command to control the onboard LED. Use the string compare function to compare the contents of the RX buffer against the string on. If it matches, turn the LED on and transmit a confirmation message back to the host over USB. Similarly, compare against the string off, and if it matches, turn the LED off and send another confirmation message. Also comment out the periodic hello world transmission we added earlier. Let's build the project now. Here we have got a few warnings. The first is that string compare function requires the string header, so include string.h at the top. The second is that string compare expects a character pointer, so typecast the RX buffer accordingly. The CDC transmit function on the other hand expects an unsigned integer pointer, so typecast the transmit strings as well. With those fixes in place, the project builds cleanly with no errors. Let's flash it to the board. Notice that while the flash is in progress, the USB device disappears from the serial monitor, but it reappears automatically once flashing is complete, without needing to reconnect the cable. This is convenient, though as mentioned, this behavior is not consistent across all STM32 boards and we will look at that difference towards the end of the video. Connect to the device in the serial monitor and send the command on. The onboard LED turns on immediately, and a confirmation log appears on the serial monitor. Now send off and the LED turns off, with the corresponding log printed as well. Sending any other string produces no response, which is exactly the intended behavior. Everything is working correctly. One of the practical advantages of using USB CDC virtual COM port communication is that, we can use it to print debug logs on the serial console using the standard printf function. To enable this, we implement a custom write function. Inside this function, we simply call CDC transmit function to send the data over the USB peripheral. Now, because CDC transmit function operates in a non-blocking manner, it may return before the entire data has been transmitted, if the USB peripheral is still busy from a previous transfer. To handle this, we add a loop inside the write function, that continuously checks whether the USB peripheral is busy, and keeps waiting until it is free before returning. This ensures that the entire data is transmitted before the function exits. Let's test this. Define an integer variable first. Now inside the infinite loop, use printf to transmit a formatted string that includes the value of the variable we just defined. We will repeat this every 1 second. Build and flash the project to the board. As you can see, the printf output is appearing on the serial console every 1 second exactly as expected. This confirms that we can comfortably use the USB CDC class as a logging interface in our projects. Now, the USB disconnect and reconnect behavior we saw on the F446 board may not be the same on all STM32. Let me demonstrate this using the Blue Pill. I already have a test project prepared for it, so let me import it to the CubeIDE, and flash it directly. The project has been flashed. Now I will connect the USB cable to the Blue Pill's USB connector. As soon as the cable is connected, the device appears in the serial monitor device list. Connect to the device, and you can see the hello world printing every 1 second. Now let me disconnect the cable. The output stops as expected. Reconnecting the cable brings the device back without needing a board reset, which is good behavior so far. Now let's see what happens when we reflash the project, while the USB cable remains connected. Unlike the F446 board, the Blue Pill does not disconnect from the serial monitor during flashing. The flash completes and the device remains listed as connected in the serial monitor. However, nothing is being printed on the console. Even if I disconnect from the device in the serial monitor and reconnect to it, still nothing gets printed. The device appears to be present but is not functioning correctly. Now let me physically remove the USB cable from the Blue Pill board and plug it back in. Then connect to the device in the serial monitor, and as you can see, the data is now printing on the console as expected. So on the Blue Pill board, after reflashing the firmware, you must physically disconnect and reconnect the USB cable before the device starts functioning again. This is likely because the Blue Pill board does not properly reinitialize the USB peripheral after a reset triggered by the flash process, whereas the F446 board handles this more gracefully. This is an important behavioral difference to be aware of when working across different STM32 boards. The same behavior applies when using the debugger as well. If you are debugging the Blue Pill board, you need to remove the USB cable first, then launch the debugger and wait until the program is running, and only after that plug the USB cable back in. Following this sequence ensures the USB peripheral initializes correctly. So to summarize, we covered how to use the USB peripheral on different STM32 boards, how to identify the correct USB port for communication, how to configure the USB peripheral in CDC mode using STM32CubeMX, and how to transmit and receive data over the USB communication device class. The CDC class is particularly well suited for printing log messages on custom STM32 boards. Unlike nuclear boards, which achieve virtual COM port functionality through UART bridged over SD-Link, custom boards can use the USB peripheral directly to implement a true VCP over USB. In the next video of this series, we will explore another USB class and build on what we have learned today. That is all for this video. You can download the project files from the article linked in the description below. If you have any questions or run into any issues, feel free to leave a comment. Keep watching and have a nice day ahead.